Welcome back to the deep dive. Now, if you spend any time at all with a large language model, chatting, coding, asking it questions,
Hmm.
you've probably hit this really annoying wall. This feeling that this incredibly smart thing just, well, forgets everything you told it the moment you start a new chat,
Yeah.
or even just clear the prompt.
Yeah, that frustration, it's not just, a bad user experience. It's actually a really deep limitation in how these AIs are built right now. Some Google researchers are calling it something like neurological anterograde amnesia.
Anterograde amnesia, like in humans.
Exactly. It's this inability for the LLM, after all that initial massive pre-training, to form new, durable, long-term memories. Its history is basically set in stone, but it's present, always vanishing.
Okay, so it's fundamentally forgetful, but they think they've got a solution, right? This thing called nested learning, or NAL.
That's the idea.
And our mission today is to really get into the core concept behind NL. They call it the unification thesis, which sounds pretty grand.
It is a big claim.
They're essentially saying that the model's architecture, the layers, the connections, and its optimization algorithm, the rules it uses to learn during training aren't actually separate things.
Right, they're saying it's like two views of the same underlying concept. And if you see that, if you see it's kind of an illusion that they're separate, then maybe you can break free from these memory limits.
So it's about seeing AI not as just static code, but as a dynamic system that learns over different timescales.
That's exactly it, moving from space to time, in a way.
Okay, let's unpack this amnesia problem first. You said the memory is binary frozen past, volatile present. Where exactly is the LLM getting stuck, based on the research?
So after pre-training, they basically have two main places to keep information. First, there's the long-term past. Think of this as static knowledge, all crammed into the frozen parameters, especially those massive MLP layers. It's there, it's solid, but you can't really update it on the fly.
Right, that's the stuff it learned from the internet, basically. Fixed.
Fixed, exactly. Then there's the immediate present. This is handled by the attention mechanism within the context window. It's incredibly powerful for understanding the current conversation.
But it's temporary, like a scratch pad.
Totally temporary. As soon as the prompt ends, poof, it's gone. They describe it as the model continuously experiencing the immediate present as if it were always new.
Because it's missing that biological process. Yeah. What was it, synaptic consolidation?
Yes, synaptic consolidation. That's the brain's mechanism for taking temporary experiences and stabilizing them, making them permanent memories. LLMs just don't have that gateway right now.
Okay, but hang on. This is where I imagine listeners are thinking, well, wait a minute. If the problem is the context window vanishing, why not just make it massive, like 1 million tokens or more?
Right.
Or what about a RAG retrieval augmented generation? That lets the model pull in external facts when needed. Isn't that solving the memory problem?
That's exactly the point the nested learning folks push back on. They argue, pretty convincingly I think, that bigger context windows, or a RAG, they only expand the volatile present. They make the scratch pad bigger.
Ah, okay.
A RAG is great for pulling up existing info, sure, but the LLM itself isn't learning anything new in a lasting way. It hasn't actually changed its internal parameters based on that retrieved info.
So we've just got a bigger temporary storage space, but still no bridge to get that information permanently into the model's own understanding, its own weights.
You got it. True. Persistent learning needs that bridge. And that's where nested learning comes in, by unifying architecture and optimization.
Right, the unification thesis. Let's get
Yeah.
to the core of that. NL dissolves this separation by looking at everything, layers, learning rules as just instances of one thing. An associative memory module. What does that actually mean in practice?
It's about defining memory really broadly. An associative memory is just some operator, let's call it M, that maps keys K to values V. And it does this by trying to solve some internal goal, some objective, which you can call math call.
Okay, I think I can see that with parts of the architecture we already know, like the attention mechanism.
Yeah.
That fits.
Perfectly. The keys and values are the embeddings of the tokens you've already processed. The query is the current token looking back at that memory. The operator M is the attention calculation itself.
And the objective math call is to find the most relevant similar tokens based on dot product similarity or whatever method it's using.
Exactly. So attention is clearly an associative memory. Now, here's the leap. The optimization algorithm itself, think backpropagation, or common optimizers like Atom, must also be an associative memory module if this unified view holds.
Okay, hold on. That's where it gets a bit abstract for me. I see backprop as math equations minimizing error. How do you map something like a gradient, which is just an error signal, to being a value stored in a memory?
This is the key insight, really. What does an optimizer do? Its job is to learn from the history of prediction errors, the surprises, and consolidate that history into better parameters.
So the history of errors itself is the memory being stored.
In a sense, yes. Let's break it down with the KV mapping. The keys, K, those are the input data points that triggered the error.
Yep.
The values, V, that's the error signal itself. The paper calls it the local surprise signal, LSS. Basically, it's the gradient.
Okay, the gradient is the value because it signals, I was surprised by this input, here's how much and in what direction. That's the piece of information being associated with the input key.
Precisely. And the operator, M, is the optimizer mechanism, Atom, SGD, whatever rules it follows. Its objective is to take that stream of surprise signals, those gradients, and compress them effectively into updated model parameters.
So the optimizer is a memory. Its internal states, like momentum buffers in Atom, are essentially its short-term memory for recent gradients.
You've got it. And seeing it this way makes the traditional distinction between architecture and optimization feel kind of artificial, doesn't it?
Yeah, it really does. Just different kinds of memory operating in the system.
And that reframing leads directly to the next big idea: deep optimizers. See, traditional optimizers like Atom or SGD with momentum, in this NL framework, they're actually quite simple associative memories. The paper kind of dismisses them as valueless or shallow, basically just linear accumulators following fixed mathematical rules.
Right. They learn according to a pre-programmed fixed strategy. They can't adapt how they learn.
Exactly. A deep optimizer throws out that fixed rulebook. It replaces the simple accumulator with a more powerful nonlinear function, maybe a small MLP, or even a recurrent network embedded right there within the optimization process itself.
Wait, so the optimizer is another neural network?
Potentially, yes. This optimizer network takes the local surprise signal, the gradient, as its input, and it learns the best way to update the main model's parameters based on that signal.
So it's not just following parameter to parameter learning gradient. It's learning a complex function of the gradient to figure out the update. It's learning to learn.
That's the core idea, learning to learn, or meta-learning baked right in.
Okay, but this sounds incredibly complicated. If you have a model learning how to update another model, isn't that just asking for trouble? Like instabilities, runaway updates, way longer training times?
That's a very valid concern. The complexity is definitely a major challenge, and we should circle back to that critique. But the potential payoff is huge because it enables this self-modifying system driven by the core engine of all learning, the local surprise signal, LSS.
Okay, describe how the LSS flows differently in nested learning compared to a standard model.
In a typical LLM, a gradient, the LSS, is calculated. It's used once, synchronously, to nudge all the parameters. Then it's basically thrown away.
Use it and lose it.
Right. In nested learning, that same LSS flows concurrently to multiple places, multiple internal optimization problems, or levels. And crucially, each level operates at a different update frequency.
That's the nested part, learning loops running at different speeds.
Precisely. You get this self-referential dynamic. The LSS hits a fast memory module, say level 1, updating it immediately to learn the specific fact or pattern it just saw.
So it learns the what?
Yes. But that same LSS also flows to the deep optimizer's memory, maybe level 2. This means the system isn't just learning the answer, it's also learning how to adjust its learning strategy based on that specific surprise. The optimizer is constantly refining its own process based on the errors it sees.
Wow, okay. That fundamentally changes the job of the AI engineer then. You're shifting from designing static things in space, like how many layers, how wide, to designing dynamic systems that operate across update frequencies across time.
That time-based design perspective is really the heart of their proposed Continuum Memory System, CMS. The CMS is the architecture that emerges from this NL philosophy. It replaces that old binary memory static weights and fast attention with a whole spectrum of memory modules.
A spectrum.
Yeah.
Now, how does that work? Give us a practical example.
Okay, remember that hypothetical logistics company LLM we mentioned? With a CMS, you'd design memory modules tailored to the different timescales of the company's data. For instance, level 0, fastest. Standard attention, updating every single token. That's for immediate conversational context.
Okay, familiar territory.
Level 2, medium speed. Maybe a dedicated domain knowledge module? Its job is to slowly learn new internal acronyms or maybe new types of shipping containers that appear in documents. It might only update its parameters, say, every 1,000 tokens processed.
So it consolidates knowledge more slowly, but still much faster than retraining the whole model.
Exactly. And then maybe level 3, slowest, a personalization module. This captures really stable things, like a specific user's delivery preferences or a major client's contact details. It might only need to update once every million tokens or even less frequently.
So the system can now actually capture information, stabilize it, and consolidate it over time, gradually, persistently, across these different levels. It finally builds that bridge, that synaptic consolidation pathway.
That's the promise. And they demonstrated this, at least in a proof of concept, with an architecture they called HOPE. HOPE is designed as a self-modifying sequence model. It integrates the CMS and this internal deep optimizer mechanism.
And they claim it achieves unbounded in-context learning.
That's the claim, yes. They report superior results, specifically in tasks that test continual learning new things without forgetting old ones, general language modeling, and reasoning over very long contexts.
We do have to add that important caveat, though. While the paper makes strong claims, a lot of the detailed experimental results supporting that superior performance are currently in the appendix or the full ArcSIF version. We're still waiting for wider independent validation.
Absolutely, that's crucial context. Good science requires replication. But even based on the theory, the potential industrial impact is pretty clear. The killer app, I think most people agree, is true on-device personalization.
Okay, why is this approach the key? Personalization right now is tricky. Either the model forgets everything, stateless, or you risk messing up its core knowledge with fine-tuning, that catastrophic forgetting problem.
It's the multi-time scale system that makes the difference. Imagine an NL model running locally on your phone. The fast updating modules, level 1, maybe level 2, can learn and persistently store personal details, your friend's new nickname, your usual coffee order, local slang you use almost instantly.
Because they have their old update frequency in memory.
Right? Meanwhile, the deeper, slow updating modules, level 3 plus, that hold the core world knowledge, they remain largely untouched by these frequent small updates. So you get genuine, immediate, persistent personalization without risking the model forgetting, how gravity works.
That really does sound like the missing piece for making AI truly personal. And if the optimizer itself is learnable, as you said, it opens the door to even more, like self-improving and self-healing systems.
Exactly. Think about the meta-learning aspect. Right now, a human engineer might have to painstakingly tune learning rates for different parts of a model or different data sets.
A nightmare, I imagine.
Yeah. But a deep optimizer could potentially analyze the patterns in the local surprise signals it receives. It might notice, for example, that gradients coming from a newly added, maybe noisy data source are really erratic.
And it could react.
It could learn to automatically turn down its own effective learning rate just for updates originating from that specific noisy module or data stream. It could make the whole system more robust, more autonomous, capable of healing or adapting itself without human intervention.
So wrapping it all together, we're looking at this grand unification, pulling together architectural ideas like Mira's and this theory of optimization as memory into one framework.
It's a really impressive theoretical synthesis, yeah. But let's bring back that healthy skepticism you raised earlier, the complexity.
It sounds elegant, but building it.
Building it, debugging it, scaling it, these asynchronous systems with multiple components learning at different clock speeds. Compared to the relative simplicity of standard synchronous back propagation, it's going to be an immense engineering challenge, a huge hurdle.
So the dream is a machine that learns and adapts throughout its life, but the reality is potentially a much more complex and difficult development process.
That seems to be the trade-off. Nested learning offers a powerful, mechanistic roadmap. It tells us how we might build truly adaptive, personalized AI by thinking explicitly about designing learning systems in the dimension of time, not just stacking more layers in space. It frames adaptive memory as an engineering problem to be solved dynamically.
And building on that very idea, that update frequency, that temporal dimension, becomes the key design parameter. I want to leave you, the listener, with a thought. We're essentially talking about designing AI using principles inspired by biological memory consolidation. If this kind of time-based design is the blueprint for a machine that can truly remember and adapt continuously, what other biological processes, what other temporal dynamics beyond just making models bigger might unlock the next generation of artificial intelligence? Something to chew on until our next deep dive.